This video is going to focus on chemical and physical equilibrium. You can copy these notes right down on your note sheet, fill in the blanks. So what is equilibrium? Equilibrium has to do with when the forward and reverse reactions occur at the same rate. It's something that we want to keep in mind as we go through. The forward and reverse reaction, same rate. It doesn't mean that we have the same amount of reactants and the same amount of products. It just means that the concentrations of reactants and products will stay constant. So you'll often hear me say concentrations constant. I constantly talk about like CC. Just remember that the C's go together. Concentrations are constant. So I'll constantly say CC. Think about maybe CC Sabathia or whoever you want to think about. But concentrations are constant at equilibrium. The amount or the mass of them is not equal. So oftentimes they'll ask you a question about this. We want to keep in mind the rates are equal, meaning the rate of going in the forward direction equals the rate of it going in the reverse direction, but the concentrations are constant. And we have different types of equilibrium systems. So we could talk about physical equilibrium and chemical equilibrium. We're going to talk about both today. So let's jump into it. First, we'll talk about some physical equilibrium. Well, we've already talked about physical equilibrium. Remember when we did our heating and cooling curves? We had our fixed points on our thermometer. So here we had solid and liquid in equilibrium with each other when you melt or when you freeze. That occurred at the melting point. And we also had liquid and gas in equilibrium with each other. So when we say that they're in equilibrium, what that means is that if we have a particular reaction, so here going from a solid to a liquid, the rate of going from a solid is equal to the rate of forming a liquid. The rates are equal, or the concentrations are constant. We've also talked about equilibrium when we talked about solutions. So we could describe a solution in terms of equilibrium as being saturated. Do you remember that? That was a word that we constantly would annotate. Saturated, meaning at equilibrium. And what does that mean is if I have let's say a solution and we have some water and we had salt. Remember when we saw some salt sitting on the bottom of the beaker? That was saturated. It was holding the maximum amount that it could hold at that particular temperature. Even if I stir this, right, I can get some of the salt to dissolve into the solution, but there's only so much, a maximum amount it could hold at that temperature, that some is then going to come back out and sit on the bottom of the beaker. So the rate of dissolving equals the rate of crystallization. Some will dissolve, but then even if I get some more to dissolve, it's then going to crystallize back out. So the rate of dissolving equals the rate of crystallization. The last example of physical equilibrium that comes up is if we were to talk about the relationship between gases and liquids within a closed container. So let's say I have a water bottle. I'm an awful artist, we know this. So, okay, yeah, that's my water bottle. And I have some level of water in there. If you were to leave the cap off the water bottle on, let's say, a summer day, we know that the water could evaporate out. So some of the liquid would become a gas. But if I have a cap on, so let's draw this as a red cap, well, I'm still going to have evaporation occurring. Some liquid here will enter the gas phase here, but the gas will then condense back to the liquid. So we have water in the liquid phase, will become a gas, but then the gas will condense back and become a liquid, so the level or the concentration of the water and gas will stay constant. You're not all of a sudden going to have a very little volume of water. So when you have a cap on, or you have a closed container, then you could have evaporation and condensation occurring at the same time here. So the examples on this slide are all physical equilibrium. Remember we talked about physical change, meaning that it doesn't change the composition of whatever it is that we're looking at. So remember melting in the first example, boiling, dissolving something, and looking at another phase change here. These are all physical processes. So these are physical equilibrium. So we could also talk about a regular chemical reaction that occur at the same rate. So chemical reactions, so for example, the reaction in the formation of ammonia through the Haber process here. See this double arrow? The double arrow just means that the reaction is at equilibrium. Sometimes you're going to see it this way. Sometimes you'll see it actually drawn with two arrows. You could see it this way. There's a couple of different notations to show you that a reaction is equilibrium, but all that means is that the rate of the forward direction, which is when we read the reaction left to right, is equal to the rate of the reverse reaction if I were to read the reaction the opposite way, right to left. So since this reaction is at equilibrium, we could say that the concentrations of the reactants and the products are staying constant, and the rate of the forward reaction equals the rate of the reverse reaction. The other thing to keep in mind that equilibrium reactions are typically going to occur in a closed system. If the system is open, meaning particles, gas particles here would be able to leave the system and it wouldn't stay at equilibrium. So another condition for equilibrium is a closed system.